right, Robertino?
Yes.
Okay, let's start with that then. Let me share my screen. Right, so this is assignment, was it 3? I mean, no, assignment 2 probably, but it's called O3.
Yes.
Anyway, the one with the data types, tables, and transactions. And I'm now in the tables module. And I open my REPL. And let me load tables. Okay, so I'm in here now. And I think in principle we have done all of that in the lecture, but I'm happy to do it again. So it was lookup and delete, I believe. So you right? Okay.
Yes.
Okay, so let's start with delete. Why not?
Sorry, insert. No, lookup.
Okay.
Yes, lookup and delete. Sorry.
No problem. Okay, so delete. Let's start with delete then. And yeah, whatever. Right. So we have an equality constraints on keys, and we have a key and a table, and we want to delete if there's an entry with this key, then we want to delete it. And because of the way we implemented it, there could also be several entries with the key, because when we inserted an existing key, we didn't remove potentially already existing keys, but just basically shadowed them. So it can happen that the same key is there more than once. And on delete, we have to delete all of them. Otherwise, we would unshadow an old one, basically, which is probably not what we want. Right. So I have a function of 2 parameters. Let's say k and t for table. Right. Of course, in this form, I can't do anything because I obviously have to somehow look at the table. So I must split on cases, on constructors. However, the key type is completely opaque. I mean, that is polymorphic in K. So I have no information about that. And in particular, I don't know what the constructors are. So there's no way for me to do anything with the K parameter. The table one, however, I do know what that is. That's a do type wrapper around lists of pairs of K and V's. So I can pattern match on that, but it's only one equation. I mean, there's only one constructor, so we still only have we still only have one equation, but I can pattern match on the table constructor. So instead of just T, I can pattern match on the table constructor, and then I have an XS, which is a list of key value pairs. Okay, so now I still can't do anything. I mean, this doesn't give me any more information than I had before. So what I really have to do is like destructure that list. I mean, make a case distinction on that list, whether it's empty or not. I mean, there are several ways. I mean, one way would be like this. So I have the case of the empty list and I have the case of the non-empty list. I mean, that's perfectly fine. Maybe just for giggles, I could also use the case command. We have seen that already, haven't we? The case statement. Does anybody remember?
I don't remember.
Right, maybe whatever. Even if you haven't, then maybe now a good time. So I can do that. It's perfectly fine to do it like this and then work on those two cases separately. But alternatively, I think I've mentioned it in the lecture, I can also use a case statement. So this is basically an alternative to writing several equations. I can say k xs off, and now basically I can give cases for this xs, and then the syntax is I should switch off Copilot again. This is the syntax. So the patterns are on the left, and there's this arrow symbol, and then what to do in that case on the right. Let me switch off the Copilot again. So I personally always, sorry about that, but I always use 4. Most people use 2, so I'm the odd one out. So this is exactly the same as what I did before with the two equations. The only reason I find this a little bit nicer is because with the two equations I had to like pattern match on the table constructor as well twice, which I find a little bit ugly. So I mean, I personally probably write like this, but it's a matter of taste, and I think that's not important. Okay, so one more thing we can do. I mean, this is fine, but we know that this list is actually a key value pair. So I can destructure this X here further because I know it's actually a pair. So I mean, normally I would call it K and V, but I can't because this K is already in use. And I mean, this is not allowed to. I think that's called nonlinear pattern. So some programming languages actually do allow that. So something like this would mean I insist that this K is the same as that K, but in Haskell you can't. So I must give a new name to this. And I mean, a common choice in this situation is to add a prime. Okay, now I basically have destructured everything as far as possible. So I have everything accessible that I'm interested in. Right, now we can actually try to implement this. So in the case of the empty table, so where this access is just the empty list, there's nothing to delete, obviously. And the result is just, again, the empty table. So I could, for example, write table empty list. There's another thing that maybe I can also introduce at this point. I mean, equivalently, I could also have written this, right? Because I know I'm now in the case where XS is the empty list. And if I do this, that is exactly the same I started with here. And this is fine. I mean, logically, it's correct. But it's a little bit of overhead because I first basically disassemble this table to look at its constituent parts at this XS. And then I reconstruct it. So there's some runtime overhead involved in building this thing. But I mean, the thing I'm building here is exactly this argument. But with what we have learned so far, there's no way for me to directly refer to this argument because I don't have a name for it. And there's a syntax in Haskell, I can use this. So you have a name and an @ symbol, and then the pattern, and then now this T stands for this, the whole thing. So I could do this if I wanted to. So that would mean in this case, the result is what I started with. And I know I'm in the case where this is empty. Right. So this is, I think, called an @ pattern or something. So you can give names to pieces of a pattern. And this is the syntax. Right, so that's the empty case. That's easy. So now what do I do in this case? Well, in this case, it obviously depends on whether K prime equals K or not. So in this case statement, I also have guard notation, exactly the same way as I have when I use different equations. So I can split this case further by considering the case that my key is the given one that I want to delete or not. Okay. So let's start with the first case. So in this case, I found a key value pair that I want to delete. So I certainly on the right-hand side won't mention this anymore. But as I mentioned before, I'm not done because potentially there's the same key also appears in the tail of the list. So I must recursively delete there. So let's see, this is now a bit messy, I think, probably. So table, or maybe not. So now we know the dollar. So okay, let's first not do it with the dollar and then I'll do it afterwards. So what's the list? Well, I skip this pair, but I want to recursively delete here. And this is now a bit unfortunate because, I can. So if I delete K, I can't write XS now because XS is a list of key values and delete expects a table. So I can do this, but now the result of delete is a table, but now I need a list here. And I think when I did it in the lecture, I just introduced this helper function, get table or something. So we can do this as well if we want. table kv to list of key value pairs. I mean, in the lecture, I eventually came to the conclusion that it's better to change the definition of this and add an accessor function here with this record syntax immediately, then I wouldn't have to implement that by hand. So that's one option. I mean, another option would be to just use it as a local definition. So I could use a where clause and put this thing here, and then I must indent. But that's probably in this case, first of all, I get a name clash here because the access is used here. And it's probably also not the right choice because it might be useful, this get table function at other, in the other functions. And if I use it locally, make a local definition here, then it's only available in the delete. So probably that's not what I want. So it's probably better there. And I could also like do it. Okay, so if I have this now, I can do get table. Okay, and now that compiles. And that's a bit, I mean, lots of parentheses. So I would use dollars wherever I can. So let's go from inside out. So I can use dollar there, and I can use dollar there, and I even can use a dollar here. So now it doesn't look that bad anymore. So that's probably the best solution. I just want to show, I mean, you don't have to introduce this extra function. You can also solve this with pattern matching. So at this point here, where I have this, I now want to get to the underlying list. I mean, one other way is to use let. So I can do let table xs equals in xs. So basically the definition I use here for the get table, inlining that and just using a let construct that we also introduced, the second option, or the first option actually for local variables. Right, and finally, the final option would be instead of let, I could use a case, so I could also do case delete of table xs xs. Okay. Okay, this is now a name clash. Right. But I think in this, so lots of possibilities, but if I do this case or that let or the local definition, then I probably have to do the same in other functions as well. So the best in this situation is to explicitly define this get table function. Ideally, as I said, in the definition of the type itself. So just use record syntax there and define it right there. Then I don't have to write any code. But I mean, if you have to solve these assignments, of course, you are not allowed to change this definition. That's given to you from us. So in that case, you have no choice. You have to like implement it by hand. Okay, and last case, I mean, we also see that we don't care about, no, okay, now we will care. So shouldn't do premature optimization. Okay, and what's this case? So in this case, the K prime is different to K. So we do not want to remove it. We want to keep it in the table. But nevertheless, we must still recursively delete the rest. So in that case, it would be table. And now we keep this pair and cons it to the rest. Okay. And now, two things I don't like about this. So one is that I basically have this pair here, and here I reconstruct it, even though I already have it. So now that I told you about the t-at, I can do the same here. So to not have to construct this pair again, even though it's already here. So I can, for example, call that key v at. and then use that here. And the second thing I don't like is that this part here is, I need that in both cases. So there's code duplication for recursively deleting the key from the rest of the list. So this might be a good place for a local definition. Something I did wrong now, it seems. Oh yeah, because this, I shouldn't have called that XS. I should have called that something else, let's say YS, but then I must be careful. And this is a ZS. And now I must concentrate. So this is Z. This is Z and this is Y. And now there's something else wrong. Oh, oh yeah. Just a typo. Okay. Oh yeah, and in this case, we also really don't need this V because this is now contained in this KB. So I don't need the V itself. So this is maybe the solution that I would pick. Not sure. With the least code duplication and so on. Okay, let's delete. Are there any questions to this?
We have one.
Yes.
I think someone raised their hand. Adrian?
Yes. Well, I had the question, but you already changed the definition of the function. But I got another question. In this case, we're just removing one element because is there any duplicates? Are there any duplicates in this data structure, or we're just having one element for every for each number?
I mean, at the moment, this is a question one can't answer because that is part of the homework to implement insert. But if you do it the same way I did it in the lecture without the new type, there I mean, if I had to insert a key that was already in the table, I didn't bother removing the old one first. I just put the new key in front of it. So it's shadowing it because lookup always returns the first match it finds. So if there are others further down the list, then that doesn't matter. But if I do, I mean, it's a design choice. I mean, it affects insert, delete, and lookup. I mean, I made the choice that when I insert and there's a duplicate, I don't mind whether there's a duplicate key. I just slap it in front. I shadow the existing one. But then I have to be careful that in lookup, I return the first match I find. And in delete, I delete all of them, which I have now done. That's why I have to recursively call delete here. I could, of course, have done a different design choice in insert that instead of, I mean, that I check whether the key is already there. And if it's already there, I remove the old one. That would be some sort of trade-off in runtimes. I mean, in the way I did insert is O of 1 is in constant time because I always slap the new key value at the head of the list. But of course, it makes delete and so on more expensive. But yeah. Okay.
Yeah, I got another question. Well, there's not.
Yes.
This is not a question, but this is something that I have struggled with. In the alter function, we had to do it to implement the function with non-duplicate elements because we were comparing the data structure with the already built in the standard and that was something that we had to re-implement in order to get rid of the duplicates. I don't know what.
Okay, that may be, yes. I haven't thought about that, but probably you're right that you have to be careful there with duplicate keys. I mean, if you want, we can try to implement alter as well afterwards.
Okay.
Okay, and then, yeah, that can be that you have to be careful there if there are duplicate keys.
It's because we're comparing this with the standard data structure of map.
Right. Yes, I mean the semantics should be the same, of course. So it should be hidden from the user. The user shouldn't need to care whether there are duplicate keys or not. I mean, it should behave like the standard map. You're right.
Okay.
But good point. Right. So let's delete other questions. Okay, then let's do lookup quickly, or also not quickly. So the point here is I just look for the first occurrence of the key. Then if I find it, I can stop. I don't have to look further. There can be duplicates, but I'm not interested in them anyway. So let's see. So same as what I said before. I mean, I can like make that faster now. So I mean, the pattern matching is the same. I mean, exactly the same as I said earlier. So I can do it the same way, or alternative. Yeah, maybe I should do it the same way, so that you don't think there's a reason why I do it this way here and the other way there. So now table as case XS of so empty list and okay. And so that's exactly the same. I mean, that's exactly the same way I started here as well. So that's like this design pattern for tables. So each data type basically comes with its own way of pattern matching or of defining functions. That's what we call this standard design pattern. And so this is what I'm doing here. So I mean, this is basically that for tables. Therefore, it's a surprise that I do start the same way for delete and lookup. But now, of course, the right-hand sides are different. So in the empty table, I obviously can't find my key. So I must return nothing. And again, as before, it depends. I mean, the case depends on whether sorry, I mean, for the same reason as before, I must call that K. So here I must check whether the key I find at the head of the list is the one I'm looking for or not. Okay, and if it is, then I'm done. I have found the V and I don't need to look any further. So I can just say just V. Okay, in this case, I haven't found my key yet. So the only thing I can do is recursively look in the tail. Now I again have this issue. So I mean, I want to call this function recursively on the tail, but the function is defined for tables, not for lists. So I must wrap that in the table constructor again, the tail. Then I can call lookup K recursively on it. And that's it. And again, I can save a parentheses by using the $. So that would be lookup. Are there any questions to this? Okay, and it's a little bit hard to test now because we haven't implemented insert, although, I mean, maybe I should do that quickly. It's more fun. And empty also, I mean, this is just a one-liner. So empty is this one with the empty list. And insert key value into a table. We said we don't mind if they're duplicates, so I can just slap the new key value pair in front of the existing list. And now that I have insert and empty as well, I can. So this is the design decision now that I don't care whether the K already appears in the access. I mean, as I said, it's a trade-off. Anyway, so if I do this, I can build an example list. Let's say keys are, I don't know, characters and values are integers or ints. So I can build a table, an example table. I insert x42 into y7 into x0 to empty. So now, let me do this again. Just specify that's int. Okay, so now I have that, and we see this design. I mean, the consequence of this decision. So I mean, you must read that from right to left. So first I inserted x with the value 0, then I inserted y with the value 7, and then I inserted x again, but now with the value 42. So the expected behavior is that this 42 replaces the 0. Now we see in our internal implementation that the 0 is still lurking around there. But if I now look up x, I won't see the 0. I get the 42. So if I try look up x in this table, I get just 42. So that's fine. That's the correct behavior. And if, of course, if I look up y, then I get the 7. And if I look up something that doesn't exist in the table, then I get nothing. So that's good. And now, I mean, if I delete x from the table, then something is wrong, because this one should also have gone. So I made a mistake somewhere. I thought I did call it recursively. Here, it's just a typo when I renamed stuff. So this is Z, it's not Ys. But this also shows it's always good to test stuff. So because I reload, I have to do my definitions again. So I redefine table. Now it's correct. So the mistake was I renamed that at some point, and then I forgot to rename this occurrence. So this must be this one here. Okay, so it's good that I checked. And that seems to behave correctly. So if I instead delete the y, then it just keeps these two occurrences of the x. But this second one doesn't do any harm. That's forever shadowed. So it's unobservable, basically. I can never get to it again, which is what I want. Okay, I'm not sure. Do you think I should do this or try this alter thing as well?
Not sure. Just not many people reach that point, so I'm not
so
sure.
Maybe
Yeah.
Okay.
I mean, the homework is due today, so they won't like submit it anymore, or maybe late. But I think like most people got like stopped at the delete and look up and delete points.
Okay.
And a few redefined. At some point we have which function was it? Add maybe, which is in the data types one, or
let's see. Let's find it. Sounds reasonable to. Okay, that is.
yes. So the ask is to re-implement add maybes using lift maybe that you like defined before.
Okay. Yeah.
And
I see. Okay,
yes.
I see.
And so some people like define the add function, which is equal to plus, to be then lifted with lift maybe.
I see.
Yeah.
I see. Okay, so let's do quickly. I mean, the lift maybe Okay, so I mean, the vanilla case, the good case is when I get a just A and a just B, because in that case I can apply F to A and B. And in all other cases, I can't, so I have to return nothing. So that's lift maybe. And then, okay, the add maybe. Right, and then, okay, and the ask is to do it in terms of lift maybe. And this is, I mean, an one-liner. I can just do this. So this lift maybe is more general. And yeah, here I don't need the F anyway. Right, and so that's easy. But I mean, in order to understand that, you must realize that, I mean, operators, I mean, the only difference between operators and named functions, I mean, functions with like letters, is, as I explained as well at length in the first introductory lecture, is that these normal functions with lowercase letters that start with a lowercase letter, they are normally, I mean, by default used as prefix, and the operators are by default used infix. But they are still functions. So the only difference is how you use them. And I also explained that you can change both of that. So I mean, the normal way we use plus is, I mean, it's always annoying because of these type notations. But if I want to add 3 and 7, I mean, the normal way to write that would be this, infix. So first argument, then the operator, then the second. But as I explained, you can just as well use it in prefix notation if you wrap it in parentheses. You can also do that. And the same is true for functions in the other way around. So if we have a function like elem that checks whether a given element is in a list. So for example, I can check whether the character S is in this list of characters Haskell, and I get true. If I want to write this infix, then I can if I put it in backticks. So this is not single quotes, that backticks. And I can use it in infix as well. So you can use functions that start with a lowercase letter by default prefix, but if you want them to use infix, you must put backticks around. And operators by default are used infix, but if you want to use them prefix, you must put parentheses around. But it's still just a function. And I can, for example, ask for the type of plus the REPL, and I see provided A is a numeric type, it's a function of type A to A to A. And therefore I can, for this add maybe, just use lift maybe and specialize to plus, to the plus function. And of course, I could also do like lift maybe multiplication to do, I mean, that would also be, why is it maybes? I think sorry, I'm still in the wrong module, so I need to load data types. Yeah, okay. Right, and this add maybes that are now defined, we can check that it works. So if I try it with just 3 and just 7, I get as expected just 10. But if one of the two or both are nothing, then I get nothing. So exactly the expected behavior. Are there any more questions about this?
Not in the chat.
Okay. Good.
Okay,
So
yeah, that was it. That was it, I think. Thank you, Lars.
Okay, very welcome. Then let me close this and let me. Is this the right one? Yeah. Okay, that's still open from Wednesday, I think. So we were in the lecture. Let me open this. Right, and just a very brief recap. I mean, we talked about function composition and currying, but then we went to this capturing design patterns, and we looked at lists. and we came, I mean, the standard design pattern on list was to look at the empty list case and the non-empty list case. And then we abstracted this pattern and we arrived at fold R, right fold. And then we had some examples how you can write a lot of things as right folds. And then we looked at the different pattern, which is very common for lists, that so-called accumulating parameter pattern, where you have an accumulator that has an initial value and you have a list, and then you basically from left to right update the accumulator until you are through the whole list. And if we do basically the same thing we did for fold right, abstract that pattern, we arrived at fold left fold. And I mean, so one way to picture that is like this. So fold right starts with the initial results E at the end, and then basically go from right to left, updates that until we get the final result. And fold left starts at the left. Hence the names fold right and fold left. Okay, so that was that. And then we did some experiments with timing and memory, and we saw that it's somehow behaves much worse than I think it should. And that led us to this problem of thunks, that because of laziness, if you have computations like that add up and you don't evaluate intermediate results, if you just, I mean, because of laziness, you normally don't, then you end up with these big chunks in memory. That can be useful. I mean, Haskell laziness is beautiful for a lot of use cases, but sometimes it's counterproductive, like in this pattern, in this accumulator pattern, because we know we want the computation to be done. I mean, we want the final value of the accumulator. So there's no reason not to evaluate it as soon as we can. But until this point in the lecture, we had not learned how to do that in Haskell, because that's like a side effect. I mean, normally there's nothing in Haskell you can do to force Haskell to evaluate stuff in a certain way. But there is a primitive, and that's called seek, which does exactly that. So it enforces, I mean, if somebody wants to evaluate B, then seek guarantees that A is evaluated first. And that leads us to this thing that's called fold left prime, which uses seek, but in this form here, it uses it under the hood using a language extension that's called bang patterns. So you can put this bang, this exclamation point, before a pattern, and that basically introduces a seek. So, I mean, it means that this egg prime will be evaluated before the computation continues. And with that, I mean, we were much faster and used less memory. But I think that's where we, and I still get that, as far as I know, there's almost no use case for fold left. You should always use fold left prime. And I think somebody, Adrian, also shared a link from WellType where they discussed this, fold left versus fold left prime. Okay, so that was that. So the idea that we have these standard design patterns on functions, I mean, like we saw for our table function now as well. So if you work with one data type and write functions about this data type, then you will often find that you always use the same pattern. I mean, the number of equations corresponds to the number of constructors and so on. And if there's a recursive position in one of the constructors, then normally you call the function will also be recursive. And example of lists, we saw that we can abstract that pattern, make it explicit. So the manifestation of making the standard design pattern on lists explicit is fold R. So another way to say that is whenever you use the standard design pattern on lists, you can equivalently also use fold R. And we're discussing that, what the benefits and the problems are. So using fold R explicitly gives a hint to the reader of your code that you are using the standard design pattern on lists. So that helps, because if people have understood that once, so they accept that, I mean, what the pattern is, understand it, then by using fold R, you basically take cognitive load from them, because they don't have to look at the equations and first understand that this is indeed the standard design pattern. Nothing funny is going on. On the other hand, we saw examples where it looks a bit complicated and where just using the standard design pattern on lists directly looks nicer or is clearer. Okay, and now the idea is to see that lists are not at all special in this regard. I mean, lists are, as I said in the beginning, like the workhorse of functional programming, so they are used a lot. But in this regard, to standard design patterns, there's nothing special about lists. So the idea is now, let me just see, right. Right, and there's actually nothing special in this. So for example, fold R replaces data constructors by suitable functions and follows the structure of the data type, just like the standard design principle. So we saw that one way to look at fold R is that each cons is replaced with the function you give as the first argument to fold R, and the empty list is replaced with the second argument you give to fold R. Or elem, for example, the elem function we saw for list just traverses the data structure and checks that it finds an element, a particular element. A filter traverses the data structure and only keeps those elements that satisfy a certain property. Or map traverses a data structure and produces a new structure of the same shape. So in the case of lists, a list of the same length, where the given function is applied to each element in the list or in the structure. And because this is not intrinsically linked to lists, it could apply to other data types, containers as well. There are type classes for that, and one of those we already mentioned in the introduction, that's the so-called foldable class. So foldable, the way to think about foldable is something that, I mean, like a container type, so something containing elements of a specific type, like a list. And you can think of it something that you could convert into a list of A's. So container T of A's is something like a list of A's, or at least you can convert it in a list of A's. And it turns out that a lot of these functions we have seen now that make sense for lists also make sense for these foldables. Okay, so fold right, fold left prime, to list. So we can, this is more or less sort of like the definition, not really definition, but the intuition behind foldables, that a container of A's you can convert into a list of A's. Check whether it's empty, it's null. The length, so the number of A's in that container. Checking whether a given element is in the container. Getting the maximum element, getting the product of all elements. So all these things not only make sense for lists. So in principle, you can imagine that you could implement them by just first using toList to get a list and then just use the list functions on it. Okay. And I mean, one example for such a T that's foldable, we know lists, of course. So T could be the list type constructor, and then a TA is just list of A's. But we have seen other examples. For example, maybe. So maybe if I ask for, I mean, let me first ask for information on list, and I see here that list is an instance of foldable. So lists are containers, but if I ask for information on maybe, I see that maybe is foldable as well. That maybe sound weird or surprising at first, but if you think about it, you can think of a maybe as a list with 0 or 1 element. So nothing is basically the empty list, and just is 1 element. Or you can think of it as a container that can contain at most 1 A. So either the container is empty or it contains an A. So maybe is also a type of containers. So in particular, it's foldable. So that means in particular, all these functions here also apply to maybe instead of T. So you can try out some. So for example, null. is false because there is a character in this container, namely the X. Or we can do product, just let's say 42 of int. It's of course boring, it's 42, but it's nevertheless correct. Or also we can do the product of nothing, maybe int. We get 1. That's also surprising for some people that the empty product is 1, but that's the standard accepted definition in mathematics. Similar to product, you have sum, so I can also take like the sum of an empty container is 0, and the sum of a non-empty container is, in the maybe case again, boring, so it's 42. Right, so maybe as an example, maybe we can also convert it to a list. So we can do to list just X. And for that, I need to import data foldable. That's not automatically imported. Right, so we get the list with 1 element. Maybe it would be clearer with Booleans. So I can convert this to a list with 1 element. And of course, if I convert nothing, then I get the empty list. Right. Oh yeah, and then if we look at pairs, so if I ask for information on the pair type, to my surprise, or not mine, but maybe yours, I see that foldable pairs A is an instance. So this also looks weird, but this is the type where, I mean, you can also partially apply these type constructors. So normally pairs have 2 type parameters, A and B, the type of the first component, the type of the second component. So this here is the type of pairs where the first component is of type A, the second is still open. And this is foldable. And this is a bit surprising for people. So there's also some, I think, discussion or argument in the community whether it was wise to make pairs an instance of foldable. So if I, for example, do a sum of 3 and a pair of 3 and 4, then probably most of you would expect the result to be 7, but the result is 4. And the reason is that the way this is foldable, I can also do to list, and I just get the 4. So the way this is considered as a container, it's considered as a container with exactly 1 element, namely the second component. So the first component is completely ignored for the foldable instance, and the container is the container that just contains the second. And yeah, so that's that. So that's like a stumbling stone. It's a bit weird, this instance. Either is a bit like maybe, so that's also an instance of foldable, where, I mean, in maybe we saw it's a list with 0 or 1 elements, or container with 0 or 1 elements. Nothing corresponds to empty container and just to the non-empty container with 1 element. Either can be seen as a generalization of maybe, where instead of nothing, we have more information. So if you look at this, for example, this example here, so if it's a right, then it will be considered. So this will be a container that contains 1 element, namely the 3. So the length is 1. There is 1 3 in there, but lefts don't count. They are like nothing. So the length of left would be 0. It's also a bit weird. And I mean, this is all like almost degenerated container. I mean, containers that contain 0 or 1 element or exactly 1 element. A better example is tree. I just want to see whether we do it. Right. Right. So let's look back at trees. This is somehow more intuitive that a tree is a container. Right. Just where was I? Trying to think whether maybe I should start a new module. There's so much stuff in there already. Tree. Just add that here in my Cabal file. Don't have to worry about that. We talk about Cabal files later. You'll probably get errors because I haven't updated the name. I must call this tree now. Okay, let's first, when we first looked at the tree type, I also said that that will be like a running example during the lectures. So that's often a good example. So let me repeat it again. So a tree can be a leaf containing A, or it can be a node with two children trees, a left subtree and a right subtree. And just for debugging, I can derive show eq odd. Right. And we should probably have an example tree. Let's say, I don't know, tree character, or maybe int. We can have a node with two subtrees. Let's say the third one is the second one is just a leaf, say leaf 37. But the first one, let's say, is a node again with two subtrees. Let's say the first one here is a leaf, and the second one, let's say, the node again with leaf 1, leaf 17. Okay. Okay, I must first quit this and reload because I added the module. And now I can load that module. So now I should be able to see my tree. And if you want a picture, or is it tedious? So we have the node at the roof, and it has two children subtrees. The right one is just 37, the leaf 37. The left one is the left one. And that again has, so now we're here, and this has one left subtree, which is just the 0. Let me make it one longer, that's easier to draw. So there's the 0. But then we also have right subtree here. So this is now that one. And there's the 1 and the 17. And I need comments. I think like this. So this is the tree, this example tree here. Okay, I think once I wrote, it's also a nice exercise to write a function that automatically draws these pictures. It can be quite useful. Anyway, so now one thing, I'm not sure whether we have had that in the lecture already or not, but if you recall the map function on lists, so we have like map, let's say, times 3. We have, for example, numbers ints from 3 to 17. Then by mapping the multiplication by 3 function over it, each element in the list from 3 to 17 gets multiplied by 3. So we get a list of the same shape. In this case, it just means the same length. But each element has been, the function, the given function has been applied to each element. Or we could map not over the list of booleans true. And we would if we put in a list of 4 elements, we get out a list of 4 elements, but each new element is this given function applied to. And of course, I mean, in those 2 examples, we started with a list of ints and got out a list of ints. In the same here, we start with a list of bool and got out a list of bool, but that was only because the multiplication by 3 and the not functions have the same argument and return type. But take a function where that's not the case. For example, I can do map show over true, false. So I put in a list of Boolean, I get out a list of strings. Right. And now if we look at this tree or trees in general, we realize that we can do something very similar to a tree as well. So, I mean, we could have a function that takes a given tree and applies a given function to each value in the leaves. So it would basically, if we did that with this example tree for some function f, it would apply f to 37, 0, 1, and 17, but put the results at the same position. So the resulting tree would have the same shape, but the values at the leaves would be updated. It's easy to write this, and in the slides it's called map tree. So given a function from A to B, and a tree of A's, turn it into a tree of B's. And how do we do that? So we have this function and we have a tree, and we know the standard design pattern for trees because there are 2 constructors, one leaf, one notice. We have 2 equations, one for the leaf case, one for the node case, and the node case tends to be recursive in both subtrees. So if we look at the leaf case, so if we have a leaf A, well, we basically can't do anything else, or I mean, we could, but the obvious thing to do is to use a leaf and apply f to the given value of type A we found there. So this resulting tree has the same shape. It used to be a leaf, it's still a leaf, but the value has changed. And in the second case, if we have a node with a left and the right subtree, then we again produce a node and we just recursively map tree f over the left subtree and map tree f over the right subtree. So we can try this out. For example, we can now map the multiplication by 3 function over our example tree. And we get one, I mean, the example tree was this. So we get the same shape of tree, but now each value in each leaf has been multiplied by 3. And again, I mean, the function, I mean, A and B can be different types. So we also map tree show. So now each former integer leaf value has been replaced by a string. That's the result of applying the show function to those leaf values. So are there any questions for this? Right, and so we did this. And we have also seen something for maybe that's also very similar. So if we, I think we had that. So map maybe given a function from A to B's, then maybe A can turn it into a maybe B. Very same idea. I'm sure that was on the slide. So we have 2 cases for maybe, nothing and just. In the case of nothing, there is no A anywhere, so no way for me to produce a B. So I have to produce nothing. And in the case of a just A, I can actually apply f to that A and return a just. So this is, and again, I mean, if I do map maybe times 3, nothing. Of course, I get nothing. But if instead I have, for example, just 2 or just 5, that applies the given function to that. So we have now seen 3 examples: map for lists, map tree, and map maybe, that look very similar, where we give a function from A to B and then something of, I mean, a container of A's, a list, a tree, a maybe, and we produce a container of Bs of the same shape. So turn a list of A's into a list of Bs, a tree of A's into a tree of Bs, maybe A into a maybe B. And the idea how to do that is also always the same. So each element of type A we find, we replace it with the given function applied to that element. So this is something that seems to be very common. And let me just see. And actually, that's so common that Haskell has a type class for that, a very important one. It's called functor. That name sounds intimidating. That comes from category theory in mathematics, but I mean, it really doesn't mean more than this. That, I mean, you have a container of A's and turn it into a container of B's without modifying the shape. So always think of map for lists. That's like the prime example. And it's just we generalize from list maybe trees just to an arbitrary f. And we say such a type constructor f is a functor if we have a function that we call f map. So given a function from A to B, it can turn a container of A's into a container of B's, an F container of A's into an F container of B's. And so we already have seen 3 instances of functor, at least 3. List, tree, and maybe. So for lists, fmap is just the usual map. For trees, fmap is tree map. And for maybe, fmap is map maybe. And because we have this functor class and the instances, nowhere in the libraries will you find map maybe, I think, or map, certainly not map tree, because that's our own type. Instead, you can just use fmap. Just want to see, right. So the instances would be like this. So lists become an instance of functor by using map, the usual map on lists. Tree becomes an instance of functor by using map tree that we just defined. Maybe become instance of functor by using map maybe. And then there's also a, so you could do this, I could do this now. I mean, for maybe it's already defined, but for tree, instance functor tree, where fmap is map tree. Okay, I can do this. Okay, just tells me that here I don't need the f. And I can, I mean, examples before for trees like this. So now that it's an instance of functor, instead of map tree, I can just write fmap. And I get the same result. I mean, not surprisingly, because I defined fmap to be just map tree. And again, you can ask, I mean, should you use something like map tree or fmap? And this is, again, the advantage of using classes in the first place. I mean, you don't have to remember a bunch of different names, like in this case, 3 names, map for lists, map tree for trees, and maybe for maybes. You just have to remember one function, fmap. And you can use that in many, many different circumstances, because a lot of type constructors are instances of functor. So somehow it makes it easier to remember. In the case of, so strictly speaking, the map function for list wouldn't be necessary. Could just always use fmap. It's just historical reasons, I suppose, and because lists are so common that the special fmap for lists has its own name and is used quite frequently. One other thing that you find in the prelude is there is another, I mean, for f, there's this operator. It's like a dollar, but with these angular brackets around. And that is just a different name for fmap. And I use that quite a lot because I find it nicer to write than fmap. And of course, the name is not a coincidence. So on purpose, it has this dollar because it's very similar to dollar. So, I mean, with dollar, you apply a function to an element, and fmap, you apply a function to each element of a container. But it looks very similar, and I think that's quite intuitive. So we could this example, if we use this operator, we could also write it like this. Or we could do show fmap tree and apply show to all elements of the list, of the tree. And of course, we can also use it for normal lists. So I can, if I import data.character to have to upper, for example, normally we wrote map to upper Haskell to turn it into all caps. But now that we know about fmap and this operator for fmap, I can also do this and get the same result. Okay, and oh yeah, okay, before I come to that, right. I talked about laws already. We saw the laws for ORT, that a lawful ORT instance should have reflexivity, symmetry, transitivity. So an element should be equal to itself and so on. And for functor, there are also laws, the so-called functor laws. And there are two. One is that F mapping the identity should be the identity. So F mapping the identity shouldn't do anything. I mean, we can check that for this. So if I F map it, the identity function, I get the same string out again. We can also try it for our tree. If I F map the identity, I get my original example tree back. So that's one functor law. And the second functor law is if you F map a composition of function, that's the same as composing the F maps. So let's get an example. For example, I can compose, for this tree, I can first multiply all elements by 3 and then show result. And now this law says it doesn't matter in which order I do that. So I could first multiply by 3 and then take the result and fmap show over it. So null times 0 times 3 and then shown, 1 times 3 shown, 17 times 3 shown, and 37 times 3 shown. And the law now says that should be the same as if I fmap only once, but as fmap the composition of show and multiplying by 3. Right, and that's exactly the same. And if you think about it, I mean, how it's implemented, that's also obvious that that holds. It shouldn't matter, right, but nevertheless. And actually, it turns out, I mean, we talked about parametricity, and there is a nice, that very parametric functions often, like a lot, you can say a lot about them without actually looking at the implementation. So there's an interesting result for these functor laws that in principle, you only have to check the first condition. I mean, that looks very surprising. I find it very surprising, but it seems to be true. So if you just check that for your functor, this first condition holds, that identity goes to identity, then this automatically follows. I mean, that's far from obvious, but I think it's nevertheless true. And as I said before, when I talked about functor laws, so the compiler can't enforce that. So the developer is expected to do that himself on paper or in a comment. And in practice, nobody, I mean, I never did that, I think, or very rarely. But at least I think about it. And over time, I mean, if you do a lot of Haskell, you get an intuition for whether that holds or not. Right. Oh yeah, maybe at this point I also say there are languages like Acta or Idris that have a even more impressive type system than Haskell, where you can actually have the compiler check these things. So there, these laws can really be part of the code and can be automatically checked, but not in Haskell. Right, and before, okay, that's I said. This is just a way to picture this second law. So you have 3 types ABC and functions between them and the composition. And now the law says if you instead look at containers, so container of A's, container of B's, container of C's, then you can fmap g to get from here to here, and you can fmap f to get from here to here, but you can also fmap the composition. The law says it shouldn't matter if you do this and this, or if you do this. Right. And the good news is that we very rarely have to implement functor ourselves, because there is, I mean, there's not, this is not there. So if I just write functor here, it will not work, because, as I said, this deriving only works for a hand-picked small collection of classes, and functor is not one of them. However, that is one of these GHD extensions that are available. That's very unimaginatively called derive functor. So if you activate this pragma, then it should work. And now it's complaining. Yeah, because I wrote the instance by hand, so now I don't have to anymore. And I also don't need the map tree anymore, because this is now just fmap. So we can actually implement that. The same is true for foldable. You can also automatically implement foldable. However, I find that a bit, I think we should first at least once do it by hand, because there are also exercises for that later. Or is that an exercise to do that by hand, the tree instance? I know there are some exercises. Maybe it is one of the assignments.
I'm not sure. I should check. But one thing, maybe, if you don't mind, before moving on, like one important thing about the laws, like Lars says, like the compiler cannot check them, but that law, like the identity law, forces you to maintain the structure of the functor you are working with. So, but just following the types, you could duplicate values in a list, or you can change nodes to leaves. But if you are forced to follow that identity law, all of a sudden you are forced to maintain the structure of the type you're working with.
Right. So maybe I was premature when I deleted this map tree. So what Robertino is saying, I mean, in this case here, for example, in the leaf case, I mean, this is, I mean, it compiled, so I could obviously do this, but I mean, nobody was, I mean, would be stopping me to do something like this. I could do this, I mean, instead of one leaf, I could create a tree that has this leaf duplicated. And now if I apply this to, I mean, times 3 to our tree, then I get one that has a different shape. And but Robertino's point is, if I now do the identity, I don't get the original tree. I mean, I get something else. And so his claim is that by insisting on this law, things like that are forbidden. I can't do this, because that would violate the law. Right, Robertino?
Yes, exactly.
Right. I'm not sure the foldable, but I know people.
Yeah. Yes, there are, sorry, Lars. There are exercises for define foldable at the instance for foldable.
For trees?
Yeah, or trees.
Okay, then I don't in the lecture now. I thought, but I mean, if you, I mean, okay, so there's an assignment to define an instance of foldable for trees, but same as functor, foldable is also, I mean, it's the same case. It's not built in, so they are not allowed to use it in the deriving class in standard Haskell, but there is also an extension to derive foldable automatically. And if we do this, then now all these things on this slide are suddenly available also for trees without us having to write a single line of code. So for example, length, now I can check length of our example tree. I get 4. So there are 4 elements in the tree. Or I could do to list of our example tree. And again, I have to import this data.foldable. Foldable. And now I get a list with the same elements. it obviously does this depth first left to right thing. So it's 0, 1, 17, 37, which would not the only way to do this, but this is the one used here. And I can also, I mean, for example, do sum. So I can just sum all elements in the tree by using sum tree. I get 55. 0 plus 1 is 1 plus 7 is 18 plus 37 is 55, or product. And 0 because of that 0 there. Right. So this is really powerful, I think, in Haskell. I mean, in principle, you could do that in other languages as well with interfaces. But nevertheless, I think it's extremely powerful. I mean, we have this, for example, this slew of functions. And if you look in the data.foldable module, there's a lot of stuff you can do with foldables. And then by recognizing these patterns and then seeing that a lot of commonly used types or also of your own types are instances actually of foldable or functor. So you suddenly, I mean, you have immediately for your data types lots and lots of functions available that you just can use out of the box because your data type is an instance of this type class. And because of this automatic deriving for functor and foldable, you don't even have to write code for it. So you immediately have like dozens of useful functions available to work on your data types without having to write a code. And I think that's very useful and very powerful and also used often. So we have that. Right. Okay, so I should that for this. So I think we should have a break. It's roughly half the time is over. So maybe, I don't know, until 22, until 40.
Okay.
Okay. Then talk to you then.
See
Thank
you.
you. See ya. Okay, should we continue?
Whenever you're ready.
Thank you. Any questions in the meantime? Check.
Not in the chat.
Okay, good. Right. So, okay, let's share the screen again. So now the idea is to do what we did for lists. The process we did for lists to come from the standard design pattern on lists to fold R, to do that for other data types as well. And let's start very simple. Let's start with bool. So if you have a function on bool, then we saw in an earlier lecture that the standard way is we split patterns on the constructors of bool, true and false. So we have two equations, one for true, one for false. And then we can write what we want to write. Write the R that we get for true and the R that we get for false. And now let's do the same that we did to arrive at fold R. So we have these interesting positions. So that's this dot, dot, dot for the true and dot, dot, dot for false. And what we did was give them names. So let's call them then prime and else prime. And similar, same happened for fold R and fold L and so on. When we introduce these names, they basically fall out of the sky. So we would get compiler errors because they are unknown names. So the next step was we introduced it as new function arguments. So we gave the function two new parameters. And then we figured out their types. And that's how for lists we got to fold R. In this case, what are the types of, we could of course also let the compiler do that. But in this case, it's very easy to see by hand because, we want an R in the end. And so on the right-hand side, we have the then prime and else prime. So both need to be of type R. So then prime and else prime are of type R. So we can write the standard design pattern like this. And that is basically if then else. So, if we, instead of fun, call it if then else, we have exactly the same thing. So that means that basically what we did for lists to arrive at fold R, when we do the same for bool, we get to if then else. And of course, if then else is very intimately connected to Booleans. Somehow it almost, once you work with Booleans, you want something like if then else. So there's what we now saw, by way of analogy, is that somehow lists to fold R is like bool to if then else. So this is maybe simple an example. Let's look at the second one, maybe. And let's do the exact same thing. So we start with an arbitrary function fun defined on maybe A, and we want a result type R. So by the standard design pattern for functions, maybe has two constructors, nothing and just. So we normally use two equations. And for the nothing case, we must do something. And for the just case, we must do something. But the do something that we do for this case can make use of the X, of course. So if again we give names to things, we could call them suggestively lowercase nothing and lowercase just. Then this lowercase just is a function that depends on X. We can make use of the X on the right-hand side here. Again, this wouldn't compile because nothing and just now are new names that aren't mentioned before. So we introduce them as new parameters and figure out the types. So looking at this first, we see nothing must have type R. And just is a function that takes this X, and X is of type A. And the whole thing must also be of type R. So just, lowercase just, is a function from A to R. So if you fill that in, we arrive at this. And similar, I mean, in lists, call the resulting thing fold R. For bool, we could call it if then else, but I mean, if then else is built in. But for maybe, we call it maybe lowercase. And that's actually also in the prelude, I think. So that's like the fold R for maybe, or the if then else for bool. And that's a useful function. So basically it says, I can define a function on maybes, is saying what should happen, what should the result be for nothing. And if it's a just x, what do I do with the x to get the result for just? Let me just see. Maybe for, I mean, this is useful. I mean, if then else is obviously useful, but that's so ingrained in any programmer that, I mean, goes without saying. But maybe it's maybe not so well used or well known. So let's think of an example. I don't know. What can we do with maybe, let's say this default thing. So we want a function that f at, I don't know. Okay, I mean, we had this, what did we call that? I'm not sure whether we called it anything that uses default value. So I think it actually in the libraries, it's called from just. So I think we called it something else. So I think that was one of the first examples when we worked with maybe. Let me just see. I think it's not in scope. Remember, so okay, it's in data.maybe, but let's define it here. So from just, the idea is we give a default value and a maybe a and go to a. And so, I mean, we defined that in the slide. So if you have this default value and in the nothing case, we use this default value. And in the just a case, we ignore the default value and use the a we have. And then we don't even need this. That was an example we had in the lectures when we talked about maybe the first time. So I can use that. So for example, I can say my default character is, I don't know, Q. And if I have a nothing, this Q is taken. But if I have a just something, then the Q is ignored. And now we could alternatively define that more concisely with maybe. Okay, so the first argument is what should happen in the nothing case. Well, in that case, we want to use the default value. And the second argument is what should happen in the just case. So given an A, what do we want to return? Well, in that case, we just want to use that A. And now I get a warning because the compile, I mean, my editor knows that this is just identity function. So I could write it like that. And now it probably complains that that is, or it's not from just, it's from maybe. I always confused the two. Okay, sorry, that's the name. Now it probably complains, whatever. No, it doesn't complain anymore. Or is it? I'm not sure.
But I think it's because you're not using it.
Yeah, right. I mean, what is the definition of, is it from just or from maybe? No, from just is a different one. That's a partial one. So it's called from maybe. It's called from maybe. Right. Anyway, so that would be one example of maybe. And another, I don't know, do we have a good example for what to do with maybe?
I mean, divide by 0 and
right.
And you can return like a default value.
Right, I could. Yes, I mean, okay, let's find. So let's say divide by, we define a divide by function. That gets, let's say, an int and another int and supposed to be int, I don't know. So normally, I mean, I could write something like this and the compiler would accept this. No, that's not a good idea, is it? No, sorry. I mean, I wanted maybe somewhere. I know what you mean, but
Yeah.
it's fine. I just trying to think of a useful function on maybe. I don't know. I mean, this is.
I mean, a virtual on maybes, because like you can do the safe divide, and maybe if you want to actually have an int, you can apply from maybe with a default to safe divide
Uh-huh.
to extract the value. I'm not sure if that works for you.
Yeah. I think it would, but I think we can just leave it at that anyway.
Okay.
Thank you, but thank you for the hint. Anyway, so this maybe is useful, this lowercase maybe, for simple cases. Again, I mean, the same story as for fold R. Some things like this, for example, I think it's nice to write it like this, very nice and concise. There are other cases where it's more complicated, and then maybe it's preferable to just spell out the two equations instead of using maybe. And now the same we can do also for our trees. And that is not, of course, in the standard libraries, because the trees are they are a type that we defined here. So the standard libraries don't know anything about it. So let's try the same thing. I mean, if we wrote functions on tree, I deleted all of them now. But I mean, if we want to define a function on tree, so fun from tree A to as a result type R, then how would we normally do that? Following the standard design pattern. So we would consider the leaf case, where it's just a leaf of value A, and then this dot 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 depending on A, can depend on A, and then we would use the, I think in the slides it's normally written like this. So in the leaf case, we get a result that somehow depends on the value at the leaf. And in the node case, if we have a left and a right subtree, and typically the result, we will recursively call our function on the left subtree and on the right subtree, and then use the results of these recursive calls to assemble our overall result. So that's the standard design pattern. So for example, I mean, we had this map tree. I deleted it because the compiler is automatically deriving, but maybe I should just, as an example, write it again. So map tree given from A to B, tree A, tree B. So in the leaf case, we return a leaf where we apply the given function to the value we find at the leaf. And in the node case, we just we produce a node, and we recursively map tree F over the left subtree and over the right subtree, right? So that was map tree. Okay, fine. So, but that's just as an example. So now, so here we use this standard pattern. And as I said here, so I mean, here we make use of the A, and in the second case, we make use of the recursive calls. Okay, so now again, following this process that we have done before, let's give names to these two cases. And again, let's just use lowercase versions of the constructor. So I call these dots here lowercase leaf, and that's a function that can be applied to A. And let's call this lowercase node, which I apply to recursively calling the function on the left and the right subtree. So now again, I have to somehow introduce parameters for these. So I don't know yet what that is, what the types are, but I know, so I have fun of leaf and node, and that's go, where go leaf A is just this leaf function applied to the A, and go node LR is just go, sorry, it's node applied to where recursively call go on the left and on the right subtree. And now the last step is to figure out the types here, but I can also, if I'm too lazy, let the compiler figure it out. So this one here, not very smart, the compiler. Did I must save, I think. Maybe this was better. I think I make a mistake somewhere.
You have the underscore before the tree in.
Oh yes. Thank you. Yes. Right. So now I get nice help. So I see the type of leaf is A to R. And I see the type of node is R to R to R. So I want to fold a tree to some result R. So given a tree, I want to produce an R. And what this tells me is I can have a function that tells me what to do with leaves. So if I find a leaf with value A, I turn it into an R using this function. And this part here tells me what to do if I have a node. So then I recursively get the R for the left subtree and I get the R for the right subtree. And then I use this function to combine the two R's to the overall result. And this thing doesn't have like a standard name. I'm not sure what it's called in the slides. Anything? No. I mean, I would call it, I mean, you could call it kata tree or something, because these things are called katamorphisms. Right. So this would be for trees. So now we could re-implement our map tree using this kata tree. So we could, let's call it map tree prime. So I just say it's kata tree, and now I must say what to do with leaves. So if I find a leaf, an A, I want to return this thing. So if I find an A, I want to do this, leaf FA. And if I find a left and a right subtree and recursively apply map tree on them, so I get results X and Y, then I just want to do node XY. Right, and I can simplify this. So this here is obviously the same as just a node function. This, by the way, is called eta reduction. Eta reduction is, I can, it says that the function that maps x to fx is the same as f. I mean, yeah. So if I have a function f and then look at the function that maps an x to f of x, that's the same as if I just used the original function. So whenever I have something, I mean, here I had this thing, and this is just a law of how functions work, that's the same as just function itself. Okay, and this here I can also write nicer. So what does that mean? Given an A, I first apply f to it, and then I apply leaf. So I can write this nicer with function composition as leaf after this, and now something is wrong, obviously. Oh yeah, I must give the name to this function, f, okay. Right. And of course, I mean, this is maybe a bit esoteric. I mean, we could also do other stuff like, I don't know. I mean, if you want to sum all elements in a tree, I mean, it's foldable anyways. You don't have to do this by hand, but we could. So if we have a tree, let's say a tree of ints, and we want to just get the sum of all the leaves, then I could also use this kata tree. So if I have a leaf value A, what is the sum? Well, it's just at A. And if I have two subtrees and the sum of the left one is X and the sum of the right one is Y, then the sum of everything is X plus Y. And again, I can dramatically simplify that. This is just the identity. And this is just the, this is just the plus function. I mean, as I said, we have some tree anyway, but because it's foldable, but I can try it on our example tree and I can get 55. Right, and that is a general principle that given a so-called algebraic data type, so an algebraic data type is these types that we have been defining all the time with data or new type, with constructors, one or more, and so on, then you can always do this thing. So you can always go through these steps and arrive at a function like what I called here kata tree. So again, if you do it for lists, using this process, you come to fold R. If you do it for Booleans, you get to if then else. If you do it for maybe, capital, you arrive at maybe lowercase. If you do it for trees, you arrive at this kata tree. And interestingly, and I think there's also an exercise to that maybe later, you can also go the other way around. So in principle, if you have this function, you can use it to basically recover this data type. So there's a way, I think it's, I always forget whether it's Scott encoding or the one, but I think it's Scott encoding. So that's a way to actually define, I mean, if you needed to write a Haskell compiler and you are now struggling how to implement these data types, one way to do that is to use functions like these. Right. And actually that's even relevant for, I mean, it's of course interesting, people that like mathematics or things like that, but it's even of somewhat importance for Plutus because Plutus does that. So, right, I mean, I'm exaggerating a bit because as a developer of D apps, you never really need to know that. But under the hood, basically data types in Plutus are used, implemented, or at least used to be implemented until now, using this idea of katamorphism. So these things are called katamorphisms. And I always forget what kata means. I mean, morphism is like a map or, I mean, shape. Is it same shape or Andres always knows he studied Greek at school. Anyway, so this idea, so the idea is you have a data type, you do the standard design pattern for functions operating on this data type, you go through this process we did, you arrive at this function that extracts the standard design pattern for that data type, and those functions are called katamorphisms. So examples are fold R, this lowercase maybe, or also this kata tree.
Lars,
Yes.
it means kata. It means I just Google it. I don't know Greek. It means down and morphemes from shape. So it comes down from the shape.
Okay, that makes sense. So the shape of the data type basically gives us the katamorphism. So the shape of the data type gives us these functions. So, and then, I mean, this slide basically just says what I already just now said in words, that in principle, we can do that for every data type we want. All our example data types we have seen, we could go through this process and arrive at like we can abstract away from standard design pattern. And those functions are called katamorphisms. And often at least for common Haskell types, they are known under a different name. So we have seen examples already for lists. It's known under the name fold R. Or maybe it's known under the name maybe lowercase. For either, there's also one, and there it's called under the name either, also lowercase. And I mean, for bool, it's called if then else, and so on. And this is what I also just said somewhat cryptically. So you can go the other way around. So given a katamorphism, you can basically use that to represent values of that type. So without having the data keyword in Haskell or the new type keyword, we could still explicitly define trees or lists or maybes using catamorphisms. I think there's later a weekly assignment to that, to study that relationship a bit. But that's, I mean, not, as I said, it's normally not of practical importance for you. But it is used in Plutus, or is used until now. I think in Plutus version 3 that changes. So they use a different way to represent data types. But nevertheless, it can be used. Is there a question?
Yes, I got a question.
Mhm.
So should we take into account the constructors of the data structures that we are doing catamorphisms, or what else can we take into account to make these catamorphisms?
Yeah, so basically, I mean, if you look at all these examples, I mean, let's see, we had, I mean, then you at some point see a pattern. So we have list. I mean, there the constructors are, the constructors for lists are empty list, which is of type, let's say, list of A. And we have the cons constructor, which is of type A to list of A to list of A. And then we arrive at the catamorphism fold R. And that has type, and I forget in which way around. So this is a bit, I should have written this the other way around. I mean, this is a bit weird for me why it's this way. I mean, I would have, doesn't matter, of course. With flip, you can, but anyway, so we have these two constructors, and then fold R has type, as I just asked, the REPL, so A to B to B, and let's call that R, because in the slides we call it the result type R to list of A to R. Right, that was an example. Now bool has two constructors, true of type bool and false type bool. And the catamorphism is if then else, which goes from R to R to bool to R. Stupid keyboard. Okay, and then we had maybe. It has nothing, type maybe A, and just from A to maybe A. And the corresponding catamorphism is maybe. It's from R A to R, maybe A to R. And now we have trees. It has leaf from A to tree A, and node from tree A to tree A to tree A. Great. Now we had our kata tree from A to R, R to R to R, tree A. A. Okay. Okay, now nobody can see anything anymore. So let me make the screen smaller just for 1 second. Right, and there I think you can see the rules. So you have one argument. I mean, these were all types with two constructors. It's maybe a bit unfortunate, but basically, yes, you get one argument in your kata for each constructor, and if it's like true or false, or if it's non-recursive, and it always, each argument has an R at the end. And then for each argument of the constructor, it has an argument here. So, and for each recursive call, it has an R. So let's see. So leave, for example, was A to 3A. So the corresponding argument in the kata, the A stays and the 3A is replaced with R. So that's the rule, basically. So you have these constructors, they A's and R, A's and type itself appear there. So basically the type itself is replaced by an R and the A stays in A. So for example, here the node constructor has type 3A, and the corresponding argument in the kata, then each tree gets replaced by the result type R. You look at just, goes from A to maybe A, so the corresponding argument in the constructor, the A stays, and then maybe R is replaced, maybe A is replaced by an R. Or here the cons goes from A to list, so in the corresponding argument in the kata, it becomes A to R. Basically, one argument per constructor, and in the constructor, wherever we used to have the data type itself, that gets replaced by R, where R is the result type. So that's how, I mean, there's a very close correspondence between these two, as you can see. Does that make sense? So it's mechanical.
Yes.
You can basically mechanically do this. And actually you can do that in Haskell. So you could basically do that automatically. So given a data type, you can automatically derive its catamorphism. And given the catamorphism, you can automatically define a data type. And that's like, works in both ways. But for that, we would need stuff that we haven't talked about yet, so-called higher rank morphism and so on. But in principle, it's possible. So we can go in both directions, from a data type to the catamorphism, and from the catamorphism back to the data type. And just, I mean, it's not really practically useful for you, but it explains this zoo of functions somehow. I mean, for historic reasons, they all have like different names. I mean, they're not called kata or anything. I mean, they have like fold R, if then else, maybe. There's also either. So it's, maybe I should add either because that has two, I mean, that's a little bit different because it has two type parameters. Did I destroy anything now? No. So we haven't seen that, but it has this left, goes from A to either A, B, and it has right, goes from A to, from B to either A, B. And then the corresponding kata is actually called either lowercase, and it takes A to R and B to R and goes to either A, B to R. Oh yeah, now that, I mean, these, as I said, all examples with two constructors. So let's just do one with one constructor, namely pairs. We have pair AB, or the pair constructor. So in this case, we only have one constructor that goes from A to B, and that's called also pair. Takes an A and a B and constructs a pair of an A and a B. And in this case, the kata also only has one argument. And let me see, that also has a name. I think it's called prot. Not completely sure. So this is from A to R. Oh, no, not prot. That's curry or uncurry. Sorry. The two. Sorry, forget about prot. And I always forget which is which. So it's the other one, uncurry. Well, it's also actually a good example. Yes. So sorry, not prot, uncurry. So I mean, the point is just also to show you. I mean, there are these functions I've looked at before, And a lot of them suddenly, I mean, if you understand, or I mean, it's just some means for your mind to bring order into the zoo of all these functions. I mean, it's maybe helpful or interesting to know that a lot of them are actually katamorphisms. They come in different shapes, and when you first see them, you don't see any connection between, for example, uncurry and maybe or so. But it turns out they're all just katamorphisms for their respective data types. So particularly, yes, uncurry is the katamorphism for the pair type. So that basically then, and that's what I said earlier, that there's a very close, you can go back and forth, that in this case, basically this back and forth is given by the fact that in uncurry are inverse to each other. Okay, that's maybe enough. I mean, it's more of, as I said, it's not so much of practical importance for you. It's just maybe interesting to get some order and structure into all these functions. And these katamorphisms tend to be all over the place and tend to be important. So that helps understand why functions like, I made a spelling mistake here, like maybe and either and uncurry and fold right and if, then that's why they appear so often. So one of the reasons, like the underlying hidden reasons, is that they're all katamorphisms. Okay. That was that lecture. Are there any questions at this point?
Seems that not.
Right, I have no idea what the next lecture is. That was number 4, right?
Yes. Let me check.
I mean, I'll see it in the... it seems, oh yeah, no. Oh yes, packaging and tools. So that's quite good because this, I mean, this was very theoretical now and maybe a bit abstract for some of you. So packaging and tools is delightfully practical. So maybe it's a nice change. Let's see. Right. I'm not sure what it, okay. Sure, there are many slides. I think there are not. There's just nothing, basically. Okay. So we want to talk about modules and packages, Cabal, library and package.
You're not sharing, Lars.
Yeah.
Oh, sorry. I'll share now. Right. So it's called. So this lecture is very short. So maybe we can even finish it today. And it's like a nice contrast, I think, because it's much more practical than what we just talked about. Right. So the idea is to talk about modules and packages. I mean, a lot of that I've already said, but nevertheless. Then talk about Cabal, which is like two different things, which is a bit confusing. And documentation. I've already talked a bit about that. Okay, so let's see. So let's start with modules. So the unit of organization of Haskell programs is called module. And module names start with capital letters and are hierarchical. So there can be several levels and they are separated by dots. So data.list would be the name of a module, or control.concurrent.async. And there's a strict one-to-one correspondence between modules and files. So each module is in its own file. I mean, I know, and I think in like C#, for example, you can, I mean, even though normally you would put one class per file, I think it's allowed actually to have more than one class in one file. In Haskell, that's not allowed. So one module, one file. And the module name must correspond to file name. And the hierarchy corresponds to folders. So in this example, in this one here, this module would be, so at the top, I mean, somewhere there's the source code of your project is, so there would be a subfolder called control, capital. That control folder would contain another folder concurrent, and that folder would contain a file async.hs. And that's, I mean, that's how it must be. So you have no freedom there. So the module structure perfectly corresponds to the file structure. And furthermore, there is, if you have like an actual program, not just a library, but something you want to actually run on your computer, like an executable, then there must be a module called main. And that module must contain a function called main. And we'll talk about that in the next lecture when we talk about side effects and I/O. So that's modules. I mean, in the examples we have seen so far, it was a bit boring because we didn't have a hierarchy. But I mean, what we just did now, for example, I mean, here were two modules. One was called higher order function, and the file name is actually higher order functions.hs. And the module is called higher order functions. And then there was a second module called tree.hs, and sorry, the second file called tree.hs containing the module tree. There can be, I mean, there could be folders, and then you would have these hierarchical module names. Right, so there's an example. So module and my module, and then normally, so it's the syntax is module, then the name of the module, then where, and then import statements of other modules you want to, I mean, whose definitions you want to use. I mean, we have seen examples of that already when we did this table abstraction. And I also already mentioned there's a module called Prelude that is implicitly always imported, so you don't have to do that. That's why a lot of functions are already available without us having to import anything. And they must be, I mean, all these imports must be at the top, so after the module declaration. So it's module, name, where, and then the imports. And I also showed you that you can, I mean, between the name of the module and the where can be a list of exports where you, I mean, if you leave that, then all the top level definitions in your module are available. I mean, maybe I should demonstrate that. So if I, so now, so if I remove this quickly, like this, if I now go to another module, if I load this, what was it called, higher order functions thing. If I now import, or okay, now in this one, for example, I could import my, sorry, I can do it this way around, of course, as well. So let's say this higher order function, I could now import my tree module. And then, I mean, this is now just so that's this stylish Haskell extension that we use that like formats the imports nicely. And right now it's gray because it says that I'm not using anything from the tree module. But now something that I did use there, I mean, I now could, for example, do whatever, foo string show tree, and remember this tree was defined. Okay, foo, whatever. So not very. Okay, fine. So this works because now I'm importing here at the top, I'm importing the tree module, and the tree module doesn't have an explicit export list. So everything I defined here in the tree module at the top level gets exported. This when I import it into a different module, I have these things available. And I say at the top level, that means all these things here, like the tree data type, this example tree map, maybe so on, but not this Go, because that's not the top level definition. That's a local definition inside this kata tree. Right, and I also already explained that you can give an explicit export list where you explicitly say what should be exported. So, and I always format it like this. For example, I could explicitly export only this this example tree, but not now these things like some tree would not be exported. So this should compile if I reload, because but if I remove this here from my export list and now recompile, then I get an error that tree is not in scope. Right. And so these import lists, so to import definitions from other modules, and you can also not, hide definitions from other modules. We have done this in this example module here. Just remove this stuff again. For example, because we defined our own fold right, but fold right is already defined in the prelude, so we would get a name conflict, and I explicitly hiding these definitions from the prelude so that I can write my own versions of that. Okay. Okay. What's the what that is now good for? Does anybody have an idea why these slides are here?
No.
Okay, let's just ignore that. It's a bit strange. Oh yeah, and there's more to say. And according to the slide, I shouldn't talk about that now to not confuse you. So you can also do so-called qualified inputs. So sometimes you want, sometimes you have two modules like written maybe by different people where the same name is used. And in Haskell, a name must only be in scope once. If it's in scope twice and you try to use it, then you get this error that it's like duplicate name or ambiguous name. But sometimes you are in a situation where you want to use both. Maybe Robertino wrote a very cool function called foo, and Karina did as well. And in my module, I want to import both of them and use both of them. But I couldn't because I get a name clash. And that's what these qualified imports are for. So then in that case, I could do something like import qualif. Maybe we can just do that. I think we have enough time. I just don't know whether I should do it in this thing. Maybe I should write just new stuff. So let's just class Karina.
We also have like a sort in map and list in data list.
Yes, but we haven't talked about map yet, I think, right?
Right. No, we haven't.
Otherwise, yes, that's like a canonical case. So let's write a bunch of modules. Robertino, where? Module, where am I? Karina, where? And me. So we'll talk about Cabal files in a second. So I won't explain this now, but I must list these things here as well. Right. Now I probably should close this and reload. And let's load this last module. Fine. Okay, so far so good. Now they don't do anything. I mean, they don't export anything. Okay, and now this example. So let's say Robertino defines a function foo from to int foo n equals 1 plus 2 times n. And say Karina defines a function foo from int to pool foo n kleiner minus 17. Sorry. Okay. Far too good. And I mean, that's no problem. I don't know why this is now. Okay. Okay, so far so good, and that's perfectly fine. I mean, obviously people must be able to use the same name because you can't globally enforce that no name is ever used twice. But now the problem starts if I want to use those. I mean, right now, if I'm now in the last module, so if I ask for the type of foo, it just says the compiler doesn't know about foo. It's not in scope. Okay, fine. So I can import Karina, and I can import Robertino. And if I now ask about the type of foo, now I get another error, ambiguous occurrence, and it says it could refer to Karina.foo, imported from Karina, or it could correspond to refer to Robertino.foo, imported from Robertino. So I mean, if I only use one of the two, it's perfectly fine. So if I only import the Karina module, then it gives me the foo, Karina's foo with her type signature. And of course, I could also import Robertino's module. And if I now ask for the type of foo, it's his foo from int to int. But now let's say I'm in a situation where I want both. And this doesn't work. And this is where qualified imports come in. So in its simplest form, I can just put the word qualified there. This is also the reason why stylish Haskell leaves this gap there, because. And now what happens now is, now if I ask for the type of foo, it doesn't know it again. But now, because what this qualified does is now I can't call it foo anymore. I must qualify it with the name of the module dot. So now I have a Karina.foo in scope, and I have a Robertino.foo in scope. And now I can use it. So I can write bar, for example. You can say bar n Karina.foo n gleich Robertino.foo. What otherwise 2. And this now compiles. Doesn't because must apply this to something. Okay, this now compiles and I can run it on stuff. I mean, the condition was less than minus 17, so I will always get the minus, always get the 42. But if I do something with minus 100, then anyway, right. So that's that. And I think actually I delete this again. I think that still compiles. Yes. So I'm always allowed to qualify. But what this qualified word, so I could have done it before without the qualified keyword, because I can always refer to names by qualifying them. But what this keyboard does is it forces me to qualify them. So now the simple foo is no longer allowed. I always have to qualify it. And then there are some variations to this. So one is that this can become very long. I mean, remember, module names can be hierarchical. So it could be data.haskell.version2.carina or something like that. So I would have to write a very long qualification. Module names can be really long in Haskell. And for that, there's also this variation where you can use as and then give it another qualification. So very common is, for example, to just use one letter. It doesn't have to be one letter. It can also be whatever. And then now this won't compile anymore, I think. Right, because now it doesn't know the Carina name anymore. Now I must use these qualifiers. So I can now shorten this to k.fu and robertino.fu. And for some reason, the stupid stylish Haskell in this case doesn't update it. Okay. And now this compiles again. Right, so that's using qualification. And then you can mix all these things, of course. You can hide stuff and you can also explicitly import. I mean, if you can just import the full module. If I do it like this, then the whole module is in scope. Everything defined in the module is imported. I can also be explicit about it. So Robertino mentioned, let's say, go to lists. In this case, I just return that. But in this case, I want to sort the list contains 1, 7, and this thing. If I do that, does it work? No, because sort is by default not in scope. It's not in the prelude. That is in data.list. So I could do import data.list. Now this will compile. I can also be more explicit and say I don't want everything from data.list. I'm just interested in the sort function. And that will now still compile because I'm not using anything else. And that's actually recommended. And like by default, this stylish Haskell or like this Haskell language server also encourage you to explicitly export. It makes this longer. I mean, some people that don't like Haskell make fun of Haskell because this can be very long. I mean, there can be pages and pages of imports. And it makes it much longer if you explicitly list everything explicitly that you import from a module. But for a reader of your code, it can be really helpful because let's say, I mean, I read some code and then I hit this spot and I have no idea what sort does. So I want to, for example, look up the documentation. If I had just imported the whole, I mean, in this case, I mean, let's say I can also import something else like whatever, control, concurrent. Let's like this, for example. I mean, now it warns me that I don't use anything from it. But nevertheless, if I had done it like this, so now I want to understand this code and I don't know what sort does. So now if I look at the imports, I don't know where it comes from. I mean, I know it doesn't come from Carina or Robertino because it's not qualified with a K or an R. But it could be in control.concurrent or it could be in data.list. And I don't know. Whereas if you use an explicit import list like this, then it's easier for me to find out where this is actually defined. I mean, I think nowadays with like editor support, even if I didn't have this, probably if I'm lucky, right now it doesn't work for whatever reason. Let me reload. But once this IntelliSense is actually working, always takes a while. I don't really know what. Okay, now it's processing. And once that's done, now it should actually work. Yeah, right. So now if I move with my mouse here, then it tells me where it's coming from. It's defined in data.oldList. It's a bit strange because I'm importing data.list. So probably data.list turn imports data.oldList. Anyway, so these days it's not so bad anymore, but I think it's still considered good practice or best practice to have explicit import lists to make it easier to see what is coming from where. And I mean, if you do like practical Haskell development, then you will have, as I said, lots of imports. So you will normally use dozens of imports in each module. So it's really not obvious what comes from where. And that can be helpful. Right, let's see. So I talked about that. Renaming modules when importing, that's this as thing, I think. You can also, I mean, we don't have to talk about everything in detail, but you can also re-export modules. So I can, for example, in my module here, I can say module, and I can export the bar function. But I can also explicitly say I want to export module data.list. And that now means that somebody importing LAS will automatically also get everything from that module. So somebody could import LAS and use the sort function without having to explicitly import data.list as well. So yes, you can do things like that. But as it says in the slide, we can mention that again when we actually need it. And right. So let's now talk about packages. So this was modules. And the unit of distribution of Haskell code is not a module normally. I think in the old days, probably when it started, people actually sent each other modules per fax or email. But I mean, these days you distribute packages. And that is not really a part of Haskell. So modules are like part of the Haskell standard. That's like defined in the language. Packages are not really Haskell. They are like a organizational structure, belong to the compiler infrastructure. So it's similar to, as I said before, for example, NPM packages for the Node ecosystem. So if you do JavaScript, then like JavaScript software, I mean, tools, libraries, whatever, are normally distributed as NPM packages. And you can compare a Haskell package with something like that. And I mean, to build stuff, we need to tell I said in the beginning, we use this GHC Haskell compiler that is automatically installed when you use one of the many options we gave you to get your working environment running. In particular, that's called GHC for Glasgow Haskell compiler, even though some people also say it's Glorious Haskell compiler. And that should actually now be installed as well. So I can, for example, call it GHC -- version, and it tells me Glorious Glasgow Haskell compilation system version 9.6.3. Right. And you can actually, I mean, that's the compiler, and you can actually use GHC to build code. I mean, to compile your code. I mean, I suppose I could compile. I don't even know exactly how it works. Right. So I could try to compile my module LAS, but now it complains that it could not find module Karina. I suppose if I try Karina, that would actually work. Yes. So I can compile, I mean, using this compiler, I can compile modules. If those modules have dependencies, then GHC doesn't find them. And I mean, there are ways to tell GHC where to look for dependencies and to compile several modules. So can use GHC to do this, but nobody does that in this day and age. Instead, people use Cabal. So Cabal is another program that's normally packaged with GHC. So when you install GHC, you normally also get Cabal, even though it's two different things. As I mentioned before, Cabal is like NPM that people use to do web development. And Cabal takes care of these things for you. So Cabal calls GHC for you with the right arguments and makes sure that all the dependencies are available, that files are compiled in the right order, and so on. And Cabal does that. I mean, if you want to build your project, it's Cabal build. Then it does stuff, and in the end, your project is compiled. And I mean, as we all know and love, Cabal also has this REPL subcommand, which allows you to open the interactive shell, and then we can interact with our code. And we saw this Cabal test command to actually, to run unit tests. Okay, but for this Cabal build to work, somehow Cabal must know what to build. What are the modules you want to build? And that's where packages come in. So Cabal thinks in packages. So basically what is built, when I say Cabal build, it's a package. That's maybe not completely true, but we get to that. So that's the unit that Cabal thinks in. And for that to work, you need a so-called Cabal file. So in the Cabal file, so in this case, our package is called higher order functions. So there must be a Cabal file called higher order functions.cabal. And then in this case, it's quite simple. So there's like a header. So this Cabal file is, I don't know, it's not YAML or anything, but it's a very simple text-based syntax, basically key value pairs. So Cabal comes in different versions. So it gives like the version we need, then the name of the package, version of the package, author package, maintainer. So that should probably be my work email, but whatever. Build type is somehow how Cabal should build it. So normally that's simple. It's this word, simple, in most cases. And then this says, okay, this is not an executable, it's library. So this package doesn't contain code that you can actually execute just like that as standalone application. Instead, it's a library that can then be used by other programs. And it lists, and there are also various things you can do, but the most important is probably this exposed modules. So it says all the modules in my package that I want to be compiled, that I want to be part of this package. And then if somebody else depends on this package, will be able to import. Then I tell, this says in which folder the source code of these files is to be found. So if you look at the tree here, so we are in this higher order function folder. So the Cabal file is in here. And on the same level where the Cabal file is also this source subfolder. And in the source folder are all my, when this was generated when I played with GHC, so I can delete them again. So there is the source code, there the modules can be found. Then come the dependencies. So we can, in a Cabal project, depend on other packages. We always depend on the base package that I already told you about, that in particular contains the prelude. And there's this weird correspondence between the GHC version and the base version. So basically, each time a new version of the GHC compiler comes out, there's also the corresponding version of the base libraries. And that must match. And this thing here, I never know, it means we need at least version 4.18.1 of the base libraries. Then this tells us what flavor of Haskell to use. So we could, what's the new one called? Is it, forgot.
2020.
But GHC or something, right? Not Haskell.
Yes, GHC, all capital letters.
Right. So there are like different versions of, over the years, some of these extensions, for example, like derived functor or whatever, they were just experimental extensions, and then some of them have later become as part of the official language and so on. So there are like different standards. So the most modern, there's, for example, Haskell 98. That was the first standard, I think. That's like vanilla Haskell. Then for many years we have used Haskell 2010. And now I think there is also GHC 2020, it's called. So that's even newer. I think if I use that, then a lot of these extensions that are now explicitly needed to activate are already automatically activated. But I think nevertheless, it's still the most common to use Haskell 2010. And finally, you can give options to the compiler. So in this case, it means switch on all warnings. So we always get these warnings here, for example, if we don't use, if we define a function but don't export it. And if I remove this warning, all warning option from the compiler options, then I think we wouldn't get those anymore. So my recommendation is always to use wall, because you want the warnings. You want to get as many warnings as possible. Otherwise, because normally they are important. I mean, often they hint at a mistake you made. I mean, if you're not, I mean, yeah, maybe we'll see examples of that. But I mean, one should always take warnings seriously. And once you have this Cabal file, then all is good, and then you can use Cabal build and Cabal REPL. And I personally could never remember these things. So I've always, I mean, in the past, I always took an existing, if I wanted to start a new package, I took an existing Cabal file and copy pasted it and then modified the values accordingly. But these days, I mean, that always existed, I think, but now it's really useful. There is something called Cabal init. So, I mean, we saw there are several subcommands of Cabal. So we have always every day used Cabal REPL to open the interactive terminal. Or yes, then told you about Cabal build to build a project, to build a package. We mentioned Cabal test to run tests. And there's also what I wanted to, Cabal init. And that will set a new Cabal project. So let's say, let me just go up one folder. So now I'm at the top level, basically, in my container. No, now I'm at top level, but let's go. It doesn't matter, actually. I can make that here. Doesn't matter, I suppose. So let's just make some foo folder here. Okay, so I'm now somewhere on my computer. I mean, actually in this container. And now let's say I want to start a new Haskell project. So instead of copy pasting like an existing one, I can do Cabal init. And then it will, I mean, you can also like call it with command line parameters and so on. But if you just do Cabal init, it will automatically be in this interactive mode. And then it will ask a couple of questions. So for example, let's say I don't want to build an executable, I want to build a library. So I say 1. And it asks, do you wish to overwrite existing files? Backup will be created. Let's say yes. There are no existing files anyway. Please choose version of Cabal specification to use. And there are several options. I mean, here we are using 3.4, so let's go with that. So that's option 6. Package name. So because I'm in the folder foo, by default that will be foo, so why not? Let's call it foo. Okay, the name foo is already used by another package on Hackage. Do we want to choose a different name? Okay, let's choose a different name. Let's call it Nairobi. I mean, it also doesn't need to be lowercase. It could be uppercase, but most packages on Haskell use lowercase names, but that's not a rule. I mean, it doesn't have to be. So let's call it Nairobi. Package version, so that will be this thing here. So I just press enter for the default. Now I can choose a license, whatever. Let's go with MIT, so that would be 4. And now what? Maybe that's because I'm in the container. Let's try this again. And normally that works. I don't know if I get this error. Let me try this again on my outside Visual Studio, just on my. Okay, let's do this again. I make a folder Nairobi. I cd into the folder. I do Cabal init. Okay, 1 for library. Yes, override. Let's pick 3.4. Use the default. Pick MIT license. Okay, now I don't know why it didn't work earlier. Anyway, now my name. Okay, fine. Email, fine. Homepage, I don't need one. Synopsis, whatever. An example, silly Haskell package. Now I can pick a category. Whatever. Let's say it's a game, 8. now the names of what I want to name the source folder, and I mean there are these options, but I'm very used to it being called SRCs for source, so I go with that default. Now I can put these language versions, as we said, the different ones. So 98, 2010. So let's go with the default 2010. Should I generate a test suite? Let's say no for now. Add informative comments. I would say no because I hate clutter, but you should probably say yes. So you see what all there is. And now it did its thing. And now if I list, so it has created basically an example project. So I could immediately do Cabal build and it will actually work. So it's a valid project with some dummy files. I can now, for example, with code open Visual Studio in this folder, and we see it. So it has created this license file and changelog file, and in particular, it has created also some example code. So one module that just defines some dummy function, and in particular, the really useful thing it has also done this Cabal file for me. And now, because I said it should provide useful comments, so it's very verbose. So it explains everything. And it has filled in the values I wanted. So the name of the package, it explains versions, the synopsis I gave, the license, where the license is, my name, my email, category, build type, blah, 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 options. So this -wall it picked by default. And it did something. So it did something else. It basically defined this common thing and then imported that so you can reuse parts of the Cabal. This example module that it created, it exposes that, picks the right version for the base dependency, says where the source files are, and default language. And that's quite useful. So you can, in a couple of seconds, basically set up a folder structure and a valid Cabal file. And then you, of course, afterwards can tweak it to what you need. So yeah, that's cool. And we are out of time. Let me just get rid of this again. And there's also this, I think it's called Cabal sdist or something. So you can actually, once you're happy with your package, you can go to Hackage. And I showed you Hackage already. So that's like the repository where you can find other people's packages. And now, for example, we could do browse package, and I don't know whether anywhere we can see how many there are, but you see there's, and that.
Yes,
oh, yeah.
at the bottom.
So at the moment there are 16,439 packages on Hackage, and whatever one we will talk about use a lot is called containers actually. So for example, we can go to that, and then you can click on it, and I showed you something like that before for the base libraries. And then, so this is like the home page for a package. This here comes in many, many versions. You can see the dependencies on other packages, the license, the author, maintainer, whatever, lots of stuff. In particular, you can see all the modules that this exports or exposes. And now we could click on one, and then we actually get documentation for that module, which is partially auto-generated. This text, of course, has been written by a human, but this stuff, these signatures and so on, that's basically auto-generated. Now we're out of time, but maybe next time I can talk a bit about these head. I mentioned that before when we talked about doc tests, but can talk a little bit about head hoc comments, how to get something like this to write your own comments functions. And it's actually very nice. When it works, it's nice. For example, does that work here? Yes. So for example, I can click on something. So I see there's this lookup LE function, and I can and that use maybe key. And let's see, I don't know what key is. So I can click on it and and then it jumps to the definition. I can also click on source and see the source code module. And even that is quite nice. So I think I can like hover here and then gives me help, tooltips and so on. So yeah, this is Hedok. And then once it's, Hackage. And once it's on Hackage, you can import it in your own modules. I mean, we will see how to do that. So in the Cabal file, the build dependencies, we only had base, but you could now, for example, also depend on containers. So you would just, at the right spot here, with build dependency, you would write comma containers, and then it would, if necessary, download this package from Hackage. But it will cache it, so it only has to download it once. And then you can use the things defined in that package. I mean, you can import it into your own modules. And so that's the most common way how to use other people's work, by depending on a Hackage package. But it's not the only way. You can also, in particular, you can depend on a GitHub project. So you're not forced to publish your stuff, your Haskell projects on Hackage. You can also put them on GitHub, and then people can, I mean, if it's public, then people can also use it as a dependency. It's a bit more involved. Then it's not enough to just write in the Cabal file. There's then a second file involved called Cabal project file, where you basically tell Cabal where to, I mean, where the GitHub repo is to find this package and so on. But that's also possible. Normally, it's not very common. I mean, for like normal Haskell projects, I mean, as far as I'm aware, people mostly use stuff from Hackage. But in particular for Cardano, it's extremely common, because IOG has written literally hundreds of, maybe even thousands, but definitely hundreds of packages. And most of them are not on Hackage, they're only on GitHub. And everything depends on everything else. So Cardano uses a lot of Haskell packages that are not on GitHub. That are not on Hackage, but only on GitHub. Right, so there's a very rich ecosystem, and using Cabal, it's easy to pull in other people's tools and libraries, so you don't always have to reinvent the wheel. So now I didn't even get through with this short tooling lecture. Okay, but I think I was anyway almost through. I think, basically, yeah. I think in principle, we can say this is done. It's just right, and we can mention other things when we come to that. But that should be enough information to get you started. So I think that's it for today, except if there are any questions. Stop presenting.
I mean, they are not in the chat, but if someone wants to ask.
Of course. Anyway, so at the moment, I mean, for now, you are never required to define your own packages. I mean, in the assignments, we always predefine the packages for you and everything already. I mean, there's a Cabal file, and the modules are there, and normally you're just required to fill in gaps somewhere. But of course, if you ever want to write your own Haskell programs or libraries, then you would need to also create your own packages. But I really think it's relatively straightforward with this Cabal init to get started. Okay, then if there are no questions, then I think we can wrap it up for today.
Yeah, I think so.
Yes, then thank you all very much, and have a nice weekend, and see you all hopefully on Monday.
Thank you. Have a
Thank
nice
you.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye. Right. Chill.